So continuing from the last class where we were discussing orientations and the utility of orientation and some of the algorithms we had seen. So today what I'm going to discuss is one of the most important work regarding the orientation studies, which was done by Alexander in 1998. Why this work was considered as the most important work? Because this work actually utilized the basic concept of cusp height, first of all, and also it considered the tessellated CAD model and the profile that was being created in order to calculate or find out the orientation. So when Alexander started his work, his basic objective was for better part accuracy and minimizing the cost of the product. So this is something which is inherently present in RP systems. When you develop a model, your idea is actually to reduce the cost. Now, the cost is basically an addition of manufacturing and the idle cost. So now when you talk of manufacturing cost, the cost of manufacturing basically reflects in time. Why? Because if you produce a part which takes a longer time, it means it is going to utilize more raw material, and more raw material means more cost. So by considering manufacturing as the criteria, he indirectly tried to alter the time concept, and the time concept basically leads to better slicing. The time concept leads to better slicing. So the whole idea actually reflects on efficient slicing in order to minimize the time. And when time is minimized, your manufacturing cost minimizes. And when manufacturing cost minimizes, the overall cost of the product reduces. So he basically worked on both the aspects of slicing as well as orientation. So slicing as well as orientation also. So when you have got an optimal orientation and you use a better slicing methodology, either adaptive or uniform, you use better slicing methodology, your time will be saved. And when your time will be saved, your manufacturing cost will reduce. And with manufacturing cost reduction, the overall cost will come down. So this was the basic concept he utilized in order to create the model. So his first concept for this part deposition orientation was to understand that what are the major sources of inaccuracy. What are the major sources of inaccuracy? So what he concluded was the major source of inaccuracy is the staircasing effect. We have all seen the staircasing effect. What happens is if we have a part like this and we start to fabricate this part is actually fabricated like this. So this is the staircasing effect that you see. And this staircasing effect actually also leads to not only surface inaccuracy, it also leads to surface roughness. So if you can control the surface roughness can be controlled by cusp height. The surface roughness can be controlled by cusp height. So he actually oriented the whole problem. Onto part inaccuracy, and part inaccuracy is dependent on surface roughness, and surface roughness is dependent on the cusp height. So again, we are going back to the slicing concept. So he established a relationship between orientation and slicing with his work, and that is one of the most important concepts or most important interactions between orientation and slicing that has ever been done. Now we all know what is cusp height. What is the cusp height? The cusp height is basically the lateral distance between, this is overhang, this is your overhang, and this is your layer thickness. So the point where the overhang joins the layer thickness, from that point, if I draw a vertical normal onto the other side of the facet, the maximum vertical distance is called as the cusp height. Now, if you consider adaptive slicing, what basically happens is the cusp height C starts to vary. It starts to vary. Now, when it varies, it becomes very difficult to determine what will be the roughness for each section. What will be the roughness for each section? It becomes very difficult because every time you need to do some calculations. So for simplicity's sake, he started with slicing with a constant layer thickness. He started slicing with a constant layer thickness, so that for a given layer thickness, C, that is the cusp height, is known to you. For a given layer thickness, C is known to you. So that is the first thing. And the second thing that he assumed was that the edges of the slices are rectangular. Now, if you remember during the slicing algorithm, the edges were actually assumed to be rectangular. It was also assumed to be parabolic. It was also assumed to be trapezoidal. But the concept of trapezoidal parabolic actually came after 2000. So since this work is prior to that, so he also considered the edges of the slices to be rectangular in nature. So what he did was he decided on a weighted cusp height. He defined a new term which is called as the weighted cusp height. Now, what is weighted cusp height? Weighted cusp height was defined as the multiplication of the area of facet with the cusp height. Now, suppose you had this staircasing. So this is one facet and this is the second facet. This is the first facet. This is the second facet. So for each facet where no support is required, that is, if I call no support, this is generally upward facing surface. So for that surface where no support is required, this is your cusp height, which is given as H. This is your cusp height, which is given as H, and this is the area of facet. So when you multiply these two, you get the weighted cusp height. Now, for a surface which is basically going to go down, what happens is like this. This is the downward facing surface. The surface normal is pointing inwards, and in this case, the surface normal points outwards. So for this type of a surface where support structure is required, the value of H actually changes to H plus R, where R is the additional increase in cusp height due to the support structure. So if support structure has to be generated, in that case, this facet will be created like this, and this is the change in cusp height. Like, I'll draw a better figure right now for you to understand. So if this is what is happening, if this is the part and you create a facet, so this will be your H. But in case a support structure is required, so this becomes your facet. So now that H changes to H plus R. So for every facet that is generated, you find out what is the weighted cusp height. So what is weighted cusp height? For a structure which requires no support, or rather the facet which requires no support, it is cusp height into the area of facet. And for facet which requires a support, it is H plus R into area of the facet. Now, the cusp height for the supported facet was actually weighted because it increases the inaccuracy. Why it increases the inaccuracy is that when you add a support structure, what happens is the support structure actually increases the surface area of that particular layer of that particular layer. It increases the surface area. So increasing the surface area will also result in increase of surface roughness, because support structure is generally prepared coarse, whereas the build structure is generally prepared finer. So definitely coarser support structure will create more surface roughness. More surface roughness means more inaccuracy. Therefore, the concept of average weighted cusp height was also introduced. The concept of average weighted cusp height has also been introduced. Now, what is average weighted cusp height? Average weighted cusp height is nothing but the sum of all the weighted cusp heights. Like over here, suppose you had 20 facets. You had 20 facets. So you calculated all the weighted cusp height for the 20 facets, and then you added it up together. Okay. And then what you did was you divided that with the total area of the 20 facets. That is 20 into area of each facet. So that is how you got average weighted cusp height. So I'll again repeat, average weighted cusp height is the sum of weighted cusp height for each of the 20 facets, and then you divided that value with the total area of the facets, that is the total area of the 20 facets that you had assumed or you had taken into consideration. Now, surface accuracy was maximized by selecting an orientation that gives minimum average weighted cusp height among the pre-selected part deposition orientations. So now suppose you have a part like this, it's a diamond. Now, how can you make this? You can keep it like this angle is 45. So one orientation can be 45-degree, another orientation can be 0-degree, another orientation can be 90-degree. So you initially selected all the possible orientations that you had. Now based on each orientation you calculated the average weighted cusp height with a predefined layer thickness. So layer thickness was predefined. The layer thickness is predefined. So with a predefined layer thickness, you calculated the average weighted cusp height for each of the orientations. And after you have done for every orientation that you wanted or that you think you can do, the minimum value of average weighted cusp height is taken into consideration, and based on that a suitable orientation is selected. So the part is made like this. So the whole idea of slicing, orientation and surface roughness are taken into consideration together in order to determine the best orientation that we can generate. One very important shortcoming of this work was that this work didn't consider the shrinkage aspect or the dimensional inaccuracy. It considered the maximum accuracy, but it is not considering the dimensional inaccuracy, which is not due to surface roughness, rather which is due to the material properties of the material properties which is being used. Hence, surface accuracy in terms of surface roughness is taken care of over here. And then they made a generic cost model. So what is the generic cost model over here? The generic cost model is pre-build preparation plus build stage plus post-processing. So definitely what is pre-build preparation? You do the machining, you do the setting of the part, and you do the processing of the part. So that is pre-build preparation. Then the building stage, where the part is fed into the machine and the part is fabricated. And then comes the post-processing stage, where the part is going to be post-processed, rather machined, or do you do some other operations on that in order to get the accurate part. So as I explained, the build cost over here is manufacturing time plus idle time, and the post-processing cost is dependent on the support material removal and the finishing cost. So this model was actually implemented on FDM machines and stereolithography machines. They developed a specific cost models for that. And orientation basically now dependent was user defined initially, user defined orientations, but optimal selection optimal selection was analytical. The optimal selection of that was done analytically using the methodology I have just explained. Now, based on the idea from developed by Alexander and earlier also, Zhu also developed a new methodology in order to determine the orientation. Now, if you remember, all the previous models were basically based on uniform slicing. Even Alexander's work is largely based on uniform slicing. Zhu actually did a lot of work from 1997 to 2002, and his work was basically based on adaptive slicing method and a CAD model which is represented by an analytical surface, a CAD model which is reflected by an analytical surface. So what is analytical surface? Now, if you define x square plus 2y square plus 3xy equal to 0, and if you try to create a surface out of this becomes an analytical surface. This becomes an analytical surface. So something like this was basically defined, and he used genetic algorithm. He developed a methodology using genetic algorithm in order to determine the layer thickness at z equal to equal contours, where z is the direction of deposition. So z axis is the direction of deposition. So initially what they did was, this work was done in two stages. So initially what they did was, for stereolithography process, as you can see also, most of the work is focused on stereolithography and FDM only. SLS and other processes came into picture later on, so their work were basically picked up from these works only. So Zhu also worked on stereolithography process, and what he did was, first of all, he pre-selected some orientations, and what he considered was build time, accuracy, and stability of the part as the criteria. Now, there are three criteria: 1, 2, and 3. Okay, the first criteria is build time, the second criteria is accuracy of the part, and third criteria is stability during the fabrication process, that is dimensional homogeneity. Now, when you are making a part, you have a total weightage of 1.00. This is the total weightage. Now you decide what is your primary criteria. If it is build time, how much weightage would you like to give to build time? Out of 1, how much weightage would you like to give? Let us assume I am giving 0.4. Then second is my accuracy, and I am also giving it an equal weightage of 0.4, and this automatically becomes 0.2. So based on this weightage factor, a formulation is defined, and for a pre-selected orientations, the orientation is investigated with respect to this part. Now, build time, they considered build time as the ratio of number of adaptive slices to the largest possible number of slices. So suppose if you have a part of say 100 mm and you have a layer of 1 mm. Okay, so you will get how many layers? 100 layers. But if you go for adaptive slicing, so somewhere you can put 20 layers, like 2 mm layer. Somewhere you can put 5 mm layer. Somewhere you can also put 10 mm layer. So now if you consider this concept with total number of 100 layers, that is the largest possible number of layers, because your minimum resolution was, let us assume 1 mm, so you could put 100 layers. So the build time is actually considered as a ratio of the number of adaptive slices that you can put to the largest number of layers. So that is 100 layers were maximum that was possible. And how many adaptive slices layer you could put? Let us assume you could put 15. So that is the ratio of build time. So that is the ratio of build time. Secondly, accuracy was estimated as the ratio of overhang area to the total surface area. So if your part is something like this, so this area is assumed to be overhang area. This area is assumed to be overhang area. Now out of the total area, this is your total area. What is the ratio of overhang area? What is the ratio of overhang area? Now if this ratio is large, you need support structure. If this ratio is very less, you don't need a support structure. So when you don't need a support structure, definitely your build time is going to come down. And when you need a support structure, your build time is going to go up. And the number of slices will also increase. Hence, your build time is also going to go up. Secondly, when your support structure is not needed, the shrinkage factor will be lesser and the dimensional accuracy will be more. When you use more material, your dimensional accuracy actually comes down, and when you use less volume of material, your dimensional accuracy actually goes up when you use plastic materials and you use resins. So accuracy was actually considered in this form, where overhang area divided by the total area was considered, and these two values were looked into as an factor. And if this factor is low, you don't need support. If this factor is high, you need support. And how they valued the stability? Now, stability was valued with the help of a penalty function, and the penalty function was actually incorporated on the basis of center of mass of the part. The center of mass of the part. Now suppose you are making a part like this. So first of all, what you did was you prepared a convex hull. So this is the convex hull. Okay? This is a convex hull. This is first point, this is the second point, this is the third point, and this is the fourth point. Let me name it P1, P2, P3, and P4. Now, what you have to check is, where is the center of mass of this whole system lying? If the center of mass lies within the convex hull, like for example, if the center of mass is lying over here, then the penalty function is different. The penalty is equal to 0. But if by some chance the center of mass comes over here, then you have to define a penalty function over here. So this is how the penalty function was incorporated regarding the stability of the part. Now, if the penalty function was to be incorporated, the value of the penalty was calculated by the ratio of multiplication of the closest distance between the center of gravity in the plane to the convex hull of the base and the height of the CG to the part to the base area. Now, what does it mean? The ratio of multiplication of the closest distance between center of gravity to the convex hull of the base. Now, let us assume this is the point, this is the base. So the minimum distance, these are the 2 points. This is point 1 and this is point 2. So the minimum distance from that point will be taken. So this is the minimum distance. And this will be multiplied with the height of the center of gravity of the part to the base plane area, yani this height. So minimum distance multiplied by height will give you the penalty function. So this penalty function was added on to the stability function. If you remember, we had taken 3 functions: build time, accuracy, and stability. So I had given zero point 0.2 weightage over here, and into this you multiply the penalty. You multiply the penalty function. Now, a trade-off among the objective was performed by choosing the suitable value of weights for stability, accuracy, and build time to achieve the best orientation. So the function became orientation. The function became orientation is equal to x1, that is the weight of build time, x2, the weight of accuracy, plus x3, that is the stability function, where x1 plus x2 plus x3 is equal to 1. So this is the function that you got, and based on this function you had to find out the orientations. So when you looked into the orientations over here, what you generally found was that these orientations were actually coming out very different when you change the weightage or when you change the penalty functions. So generally what was observed, as was observed in the previous work of Zoo also, that the penalty function was generally coming out to be zero. The penalty function was generally coming out to be zero because in 99.99% cases, all the center of masses were lying within the convex hull. All this was lying between within the convex hull. So the penalty function was generally coming out to be zero. So penalty function was generally zero, and what was found was that if you had a pre-selected orientations in your mind with respect to the part, you could almost get an equivalent function. But what was observed was generally the orientation obtained by Zoo was equivalent to the orientation that was obtained by Alexander also. The answers were coming out to be pretty similar. So Zoo's work actually faded out because his function was more complicated as compared to the function of Alexander, which was simply based on slicing and orientation simultaneously, where Zoo's function is only based on orientation. Then McClurkin and Rosen also came up with a different plan. They used response surface methodology of statistical design. They used response surface methodology of statistical designs using central composite experimental plan, and they developed basically statistical models to predict build time, accuracy, and surface finish of stereolithography parts. So what they did was they assumed layer thickness, hatch spacing, Z height, and pot volume as the variables. So they had four variables, and they developed a quadratic model for each of the output, each of the responses, the build time, accuracy, and surface finish. And what they did was they simply used a software called Minitab in order to fit the functions and find out the ANOVA table and connect the responses. The models were highly accurate. No problem with that. The models were highly accurate. But the problem was these models were actually prepared for a domain. These models were actually prepared for a specific domain. Now, what was the domain? The domain is like for layer thickness, there is a minimum layer thickness that they took because they took three spaced variables. So they took from 100 to 500 microns. So this is minimum, that is 100, and this is maximum, that is 500. But if somebody took 600 micron as the layer thickness, the models was not fitting. The accuracy of the model was not substantial or satisfactory. Hence, the models were only fitting within the specified domain of the process parameters. The range of the process parameters that was taken, the model was fitting only within that function. So it fitted in that domain very nicely. Actually, the accuracy was very high, 99% was the accuracy that they had considered. So the model was coming very good for that specified domain. But beyond that domain, on either side, either on this side or either on this side, the model was not fitting. Another aspect, another problematic part was hatch spacing. Now, for hatch space, what is hatch spacing? Now, what happens is when the part is deposited like this, when the material is deposited while layering, what happens is this is your hatch spacing. Now, as your nozzle diameter, as your nozzle diameter changes, this hatch spacing also changes. This hatch spacing also changes. So what happens is they considered hatch spacing as the parameter, but they didn't consider the volume of material being deposited at any given point of time as a variable. As a result, what was happening is part volume was coming out to be insignificant. Part volume was coming out to be insignificant. Hatch spacing was coming out to be significant. But hatch spacing is not an independent parameter. It depends upon the nozzle diameter. It depends upon the nozzle diameter. That is why later on, later on I mean after 2003, when FDM was analyzed in more depth, people understood and realized that actually it is the nozzle diameter that plays a very significant role as compared to hatch spacing. So this work is important because they used a completely new phenomena of statistical modeling and presented a model which was very highly accurate with respect to layer thickness and hatch spacing, z height of the part, also with respect to build time, accuracy and surface finish. But the models had an inherent deficiency that it was fitting only within the specified domain, and it was not working outside the domain under any sense. Under any sense.